our latest installment featuring James Stoffo. We're really excited. People are joining us. Everybody's coming in, getting logged in. We have a record crowd joining us today, which we're really excited about. This topic, there are very few topics like RF and RF technology that generate so much interest with people. I would like to point out, totally unrelated to RF, that Mac and I have taken all your emails very seriously, and we're trying a lot of different microphones, and we're putting them in the screenshot so everybody knows we're trying hard to do good audio here. But seriously, we appreciate everybody's comments. Oh, and so as to not leave Pete out of this whole discussion, there you go. Again, back to RF. This one we knew was gonna really excite folks, and that has proven to be the case with everybody that has logged in for it today, as well as registered. So, hot topics. Looking at James now, I'm going to say James is ready for hot weather. He has come completely prepared for what we're about to do today. You know, one of the things that's so neat about this industry is the relationships that we can all have with one another. I remember finally one of the gigs I worked with James was over when during the papal visit at St. Joe's Seminary, and we're setting up over in the work trailer. Pete's there, and Pete was everywhere because, you know, it's Pete. Mac was over at the 9/11. They were still building that at the time, and the illustrious Larry Estrin had brought us all together for that one. And you know, again, all these relationships that over the years, they all culminate, they come back together. When we were out there, the Secret Service was curious if our CP antenna was actually a camera, right? And we get all kinds of, you get some odd requests in our line of work when it comes to communications, but obviously James has done so much for the industry for couple generations now. I'm not trying to make you feel old, James, but you've had such an impact on people. Speaking of generations, I think you and Pete and Mac actually go back considerably further than I do. Why don't you tell us about that 1 degree of Pete Erskine separation?
Well, a long time ago, Larry had done a couple of dozen Super Bowls already, and I joined him about Super Bowl 25, 24, something like about that. And early on, one of the first Super Bowls we did, we hired James to do all of our RF down on the field. And it was at that time the NFL hired Larry to do everything, all the hotels, all the streets, all outside, all inside. So it was we had a team of close to 100 audio people, just audio, working on that. And James was the guy we found to do the RF for us, and we were very happy to get him.
Yeah.
At that time, I think Mac actually was in the rack room, working in the rack room,
right. Yep.
and James was on the field, and we went from there. So I've known him since I was a wee tiny tyke.
and you know, RF certainly in the back in that original show, RF was, I would say, on some levels more complex, not to diminish where we are today. Today has a different level of complexity, right, James? You know, we've emerged into the next generation of technology. Thank you to the cell phone industry for causing a bit of that. The repack certainly has caused all of us to become involved. You know, even myself, even though RF and communications is probably one of my most passionate things, I still spend a lot of times behind the console. But I will tell you, as a mixer, the quality of your A2, your RF coordinator, you live and die by that, because who gets the call when there's a problem? It's me. They're like, what's wrong with the microphone? Well, you know, we're a team, and that's, I think, the whole idea of these webcasts is say, look, we work across so many disciplines, so many different things. And at this point, James, I'm going to turn this over to you.
I
And
want to say one thing
you
first,
got one
Kelly.
more?
Everybody who's watching is an attendee. I just want to describe on your screens, on the right-hand side, you'll see a little box with a question mark in it. That's where you click on to ask questions. And uh, we're glad to take any question at all in there. We do sort of edit them a little bit, so questions that aren't directly related to stuff that James talking about, we may answer directly. I do say we've got two people, Patricio Ramirez from Chile is here, and Alejandro Patara is from Mexico. I'm sure I wrecked your pronunciation of your names.
Oh,
But
we have Austria too.
cool. So go ahead and put your questions in there, and Harlan will cut and paste into the screens directly in front of all of us. And strangely enough, we've already gotten 4 questions in by email, and we might as well address. Do you want to address these when we get to that section of your talk, James?
Sure. Yeah, just read them to me if if I don't get to them when we get to the
Okay, we'll
appropriate
definitely
section.
do that. We're going to start right at the top with this screen here, and I'm going to disappear, and just James is going to be on, so go for it.
All right, and as soon as we kick off into the PowerPoint, you can make my video disappear as well. Well, first off, thanks Kelly, Pete, and Mac for putting this together. You know, we're all being asked to stay at home, and we've obviously aren't working right now. So this is a great way to make the best use of our time. This time is not going to last very long, and people are going to be itching to get out and go back to the events and get back to life as normal. So the better prepared we are when that point happens, hopefully soon, the better off we'll all be when it does finally get here. And hello to everybody in webinar land. A special bienvenido to Patricio Marírez and Alejandro Peralta. One's from Mexico, one's from Chile. I know them both. Thanks for joining, as well as everybody else. So I'm going to go ahead and kick into the PowerPoint. Many of you have either presented with me or sat in on this particular discussion before. There's some basic material, and we're going to apply more of it towards the current predicament that we're in the United States. However, this applies worldwide as well. Certainly Mexico will be next. It's happening in Europe now. I think it's happening to some extent in Mexico. And that is the overall issue of frequency congestion because of auction getting spectrumed off. And this is really up-to-date information as of today. Henry Cohen, my friend and a partner in Radioactive Designs, shared an email correspondence with T-Mobile. So this info is all accurate as of just about 2 hours ago. So again, here in the United States and throughout most of the world, we've shared radio spectrum with television broadcasts in coordination and some cooperation with television broadcasts. And those of you who have heard me speak before, even when I did my first presentations on wireless back in 2000 at the advent of introduction of digital television, you know me to be one to make sensationalist comments occasionally. But it's also good to see that within a couple of years, those sensational comments proved to be correct. I don't have a crystal ball that I gaze into, but certainly we could make some assessments based on the technology being presented by people with a lot more money than the audio community has. And that first presentation about DTV, I made the statement that the next 5 years will present greater challenges to the wireless operator than in any period of 5 years in the history of man-made radio. And before the auction, I changed that to the next 3 years, which incidentally ends this July. And now I'm saying we're in it. We're actually towards the end of it. And if we can get through what's going on right now today in wireless operations, then it'll be a while before it gets much worse. That's the good news. So let me just touch real quick on these next 2 graphics. They're all words. And incidentally, anyone who wants a copy of this PowerPoint, just email us. we were going to get deeper into radioactive designs technology, but because when I started writing this, it turned out to be more of a general RF, and a lot of you probably work with wireless microphones and in-ears and don't really care much about radioactive designs or any other RF comm. What we're going to do is have a specific radioactive designs discussion at some point over the next week with the partners, Henry Cohen, probably Rich Stockton, and I'll be there. So this one will focus more on general wireless that applies to anyone using wireless audio equipment, or as the FCC classifies as low power auxiliary devices. Here you see back in June 2010, we had the 700 megahertz auction. We've all finally got over that. Everybody probably went out and purchased lots and lots of equipment above 600 meg, but below 700 meg. And that equipment is for probably about 80% worth as a boat anchor as much as anything else. We'll get to the specific bands here and the legal use of those bands above 600 meg, but we got over that hump of the 2010 700 meg auction. Now we're completed with the 600 meg auction. We've lost over 200 meg of spectrum, and all other UHF wireless short of two small bands must operate below TV channel 37, which is 608 megahertz. You call those two bands either guard bands or a duplex gap. The duplex gap is 652 to 663 megahertz. And Henry Cohen just reminded me today to make sure you knew how that broke down. 652 to 657 is reserved for part 74 only. 657 to 663, you're limited to 20 milliwatts and could be shared down the road by white space devices, which we'll talk about a bit. And VHF survived the repack. That's great news for us because VHF remains extremely open. We took a real risk with radioactive designs because after investing a large sum of money, this auction may have resulted in no VHF TV stations, in which case, if you want to see me, you'd have to come down to the Keys and hire my boat because I'd be a boat captain instead of an RF tech. But in this case, out of about 1,000 stations, only 13 moved to high band VHF, and that's why you have radioactive design packs in there. You have Electrosonics IFBs and wireless microphone manufacturers building wireless mics. Shure, I believe, has a ULXD down in that band as well. Perfectly clear band, great band to use. And then 614 to 616, which is right above TV 37, is 2 meg, and that will remain legal for the foreseeable future. The reason that will remain legal for more likely my lifetime is because TV 37 is a radio astronomy band. It's also search for extraterrestrial intelligence band, and so that 614 to 616 is the guard band to protect channel 37's operations. There's also medical telemetry in there. So this graph you're looking at, it could represent any city or any country. It's just a graph of before the auction, and it shows how much spectrum we had to operate in. And then after the auction, you could see that things become much more congested, and we see that our T-Mobile and other carriers, Dish, for example, have now energized. You could go on to Radioactive Design's website, and pretty much every major city in the country, we have what you see before you is for Washington, D.C., but for the most part, most cities have a tremendous amount of open VHF. Down there, there's not much audio equipment in channel 2 through 4, but there is TV 5 and 6, and of course 7 through 13. And DC happens to be a lucky city. There are plenty of open channels. That's rare for what's going on right now. This next one just kind of gives you a quick look at where we've come over the last 20 years, just from before the digital TV transmission to now. We've lost, I'd say 90% of spectrum to operate in that we've had since 1962. And we just need to now play every trick in the book that we can to keep our noise floor down. That's really the magic takeaway from everything you'll see in this discussion is keep your RF noise floor down. If you minimize your RF noise floor, you're going to get better audio quality out of your wireless microphones, your in-ears, your comms, and you're going to increase the actual operational range of those systems. So noise floor is the key to successful operations. And so we're going to discuss the best ways to keep your noise floor as best as it can be. Now, I wanted to take the voodoo out of this. Part of the biggest hang-up with operating wireless is many people came into this industry and had to work with wireless as an audio mixer first, in other words, from the ground up, from the audio side up. I came into this from an RF tech position and then got thrown into the audio department, right? I mean, if RF were a few megahertz higher, I might have ended up in lighting, I don't know. But as far as where they couldn't envision where to put the RF tech, and my first positions were not microphones, but communications equipment. So I wanted to take some of the black magic, some of the black art, and you don't have to, you know, get a PhD in RF to understand what it is and to know how to master it and manipulate it. So this will not be a PhD level discussion, but I would certainly say it'd be more of a BS. So if you were to take a 5,000 watt RF audio amplifier, like a Crown or a QSC or whatever, you pick your amplifier of choice, and generated into it a 5 kilohertz tone, and plugged it into a speaker, a big speaker that could handle 5,000 watts, you would get 5,000 watts at 5 kilohertz of sound pressure variations, right? You're converting energy. You can neither create nor destroy energy, however, we can change its form. If you take that same exact amplifier and instead of hooking it up to a speaker, you hook it up to a 6-mile long metal coat hanger, that energy has to go somewhere. The energy is going to send electrons. It'll be a 5 kilohertz signal, but it'll radiate out at 5,000 watts in RF, in an electromagnetic wave. In other words, you have this 6-mile long coat hanger, you're shoving an abundance of electrons into it at 5 kilohertz, at a level of 5,000 watts, and that's just simply a power level, an electric power level at a specific frequency. You put it into a speaker, it's a transducer, it converts to sound pressure variations. If you put it into a piece of metal, the metal becomes excited, the electrons have to radiate, or else it'll melt down. I mean, when I'm a scuba diver, so I can relate it to if I fill up a scuba tank and I put it out to my house here in the Florida Keys out in the sun, as the sun heats up that scuba tank, there's a relief valve to off-gas that pressure. If we don't off-gas the pressure, the tank blows up. Well, that's what happens in an antenna. You bombard it with electrical energy at a certain frequency and a certain power, and as the energy goes to the tip of the antenna and begins to return back towards the source, the antenna connection, it then radiates these electrons in the form of electromagnetic energy or radiation. We're going to talk about different types of modulation today. There are 3 types of modulation that are used in professional audio as of 2020 right now. We have digital, like a ULXD or a Sennheiser 6000 or a Riedel or a Clearcom digital comm system. We have FM, which is what we've mainly been dealing with up until just a few years ago, as far as wireless microphones and in-ears go, like the Sennheiser 1046 is an FM system, the Shure Axient systems, and UHFR. Electrosonics, of course, has lots of FM systems, and we'll talk about how to set here in just in a minute, how to set your gains on the transmitter to maximize your signal to noise ratio. And of course, now with radioactive designs, we have amplitude modulation, and people say, well, why did you go to amplitude modulation? My AM radio on my car sounds horrible, right, compared to FM. But your car radio doesn't have the DSP that we use in a RAD, for example, to make the audio sound as close to an FM system as possible. And also, our goal when we developed the radioactive design system was spectral efficiency. And being a communications device and not a wireless mic where audio has to be key, you can get away with a quality that's not as good as a microphone, as long as it's discernible and you can communicate with it. I'm not saying you can get away with it sounding horrible, of course not. But we've been able to play some tricks with AM, and again, the goal was spectral efficiency, and by using an amplitude modulated signal rather than FM or digital, we literally can pack 15 times the amount of systems into the same RF footprint. So this is a look. We have a lot of material to cover, so I'm not going to get really deep into this this graphic, other than to say that FM is not as spectrally efficient as AM, because when you modulate using frequency modulation, you may take up 150 to 300 kilohertz, whereas with amplitude modulation, you're only taking up 20 kilohertz. So going again, as I said, the FM transmitter, in order to get the best audio quality possible, the best signal to noise ratio possible, that's going to improve your audio and your range. And the reason it improves your range, because the range of a wireless receiver, whether it's a mic, a comm, or an ear, is dependent on one thing, and that is the signal from the transmitter being greater than the background noise. So theoretically, a transmitter signal will go on at infinity, but at some point that signal disappears into the noise floor. Now, you can see here, once you hand off a microphone to a talent, you lose control over how that piece of equipment is handled. I've had executives come back to me and say they dropped their transmitter in the toilet while they were going to the bathroom, and all types of things. So you have to make all of your adjustments before you hand that product off. In this case, if it's an and by the way, I want to thank Sennheiser for some earlier graphs, and I'll try to be better about thanking Joe Chowdelli, who loaned me a lot of these graphics. This one is an old Electrosonics graph. Probably Carl Winkler or maybe Gordon Moore provided this, or Bruce. But this is just showing you graphically that as you turn up, and in this case we say signal to noise ratio, that's actually the audio signal to RF noise. If you look at this, you're going to increase your range and your audio quality by turning up your FM gain on the transmitter, thereby giving you a better signal to noise ratio. But we're talking about audio signal to RF noise, right? So if you turn up your gain too high, you get into distortion, you increase your occupied bandwidth. But if you turn it too low, you'll begin to hear the background noise of coming in on the receiver. Just to give you an example, a visual of the difference between occupied bandwidth, this is a 1 meg wide window on a spectrum analyzer, and this is one transmitter transmitting frequency modulation. And what happens is, in a static environment when there's no audio, there's one small razor-like carrier in the center, and as someone begins to shout into the microphone, it begins to deviate in frequency, modulate in frequency. Now, though the legal limit is only around 100 kilohertz, because of a thing called Carlson's rule, if you want to do some further educating by yourself, the receiver requires about 3 to 4 times the amount of the transmitter deviation in order to process that signal. So that's why, even though if you looked at an analyzer, it would only look like 100 kilohertz, this is showing that the occupied bandwidth requirement for an FM receiver. Digital, it doesn't matter whether you're talking into it or not. It's a static signal. Most digital wireless microphones distributed professionally are about 210 or so kilohertz wide. So that's sounds a lot wider than an FM system. However, intermod is not as much of an issue, primarily because to make digital mics, and because they're newer, there are more linear RF amplifiers. So you can get away with lots of mixing that would occur in an FM system, but will not occur in transmitter to transmitter on digital. The next graph here is amplitude modulation. And so as you can see, looking at that same 1 meg window, we're only occupying 20 kilohertz, and that is a dual sideband system. It's because we use a Costas loop. We thought for communications, most of the stuff we do is industrial, space vehicle launches, nuke plants, things of that nature. And so life safety is critical. And so that the the Costas loop requires a double sideband radio to lock it in, and that's what you're looking at. That's two separate carriers that are centered around one frequency. It's called double sideband suppressed carrier. And if anybody wants to email questions that go beyond the 2-hour limit we have, you could email me. Kelly will put up my email at the end of this. Most of you probably already have my RF guy address. You could also reach me through Radioactive Designs or email into Kelly and he'll distribute those. And I may not get right back.
James, let
Go
me
ahead.
introduce just for a second. We've got a question. Does noise floor matter in digital radio transmission as well?
Absolutely. And you know, it's really funny. We were dying to get these systems on the market. You know, the Sennheiser 6000, great digital system. The Shure Axient Digital, use them all the time. Both of those systems, speaking in digital terms in particular. And I'll remember the first time I used, I think the Axient Digital, before I used the original 6000, which I think was the 9000. Anyway, it was an Axient Digital. And I was so happy that I didn't have to worry about interference or noise floor. You just magically throw out these systems and they work, right? No. During rehearsal, it was an executive at a Microsoft show, I believe. She was pretty far away, center stage, and I was way off stage left during rehearsal, thankfully. And she started to drop out. The mic was taking hits like crazy. And so I was able to, during a break, kill that transmitter. And sure enough, there was some RF noise on that receiver's frequency that was actually coming in through one of my own RF amps. So the first thing I did was remove the amps from the RF noise. But digital is just as susceptible to RF noise as analog. The difference is when you're operating digital systems, you don't realize there's a problem until it's too late. With analog, you have the advantage of hearing a little bit of a noise floor in the background creeping in. We used to call it pumping and breathing, a little bit of pumping and breathing, and then you know, okay, I need to take a closer look at this frequency. Digital sounds great. It's either in or it's out. And when it's out, it's completely out. Now, that might be a little less annoying than a noise burst from analog, but believe me, you get yelled at just as loudly. If you can go back to that other slide real quick, just for a second, Pete. I have this, the Zen of wireless say, one must always look at the world from the receiver's perspective. The reason that I say that is because whether you're an in-ear monitor, a comm system, a comm pack, or a wireless mic, your receiver antenna is looking at the RF world from many, many different places. If you're an RF microphone and you have your microphone receivers backstage behind the LED video wall, you're going to pick up noise from the video wall. You can move that antenna away from the video wall. It's a very near field RF energy noise. If you are an in-ear monitor, where is your receiver antenna? It's running around with the artist all over the stage and out into the audience. If you're a wireless intercom, where is your belt pack receiver antenna? It's over in a green room. It's out in the truck preparing for the next act. You know, so in other words, whenever you're setting up RF, this is the second most important thing that should be on your mind is where is my receiver antenna for this specific device? When I set up a show, I'll have many, many different devices. I'll have, of course, multiple wireless microphones, multiple in-ear monitors, and of course, many, many comm systems of various types. Yes, each one of those systems requires a different antenna position. In the case of some of the digital comms, you may have 12 or 16 antenna positions. Okay. What we're looking at here is just simply the reason for diversity. We're going to get into some diversity techniques. The graph before that was a display of what the voltage on an antenna looks like. If you can put that up just for a sec, please, Pete. And that is, as someone walks across the stage, there are certain dropouts. They're going to be multipath dropouts. They can occur for a lot of reasons. This one here, because they're so sharp and deep, I would call antenna polarity dropouts. In other words, they're happening because the transmitter polarization is off axis from the receiver antenna. And that's when you'll see those sharp dropouts. If it was more of a multipath, it would be more of a fade and they'd be much smoother dips. These are very sharp dips indicating a reason like a cross pole situation where you have your receiver antennas might be paddles, shark fins that are on a mic stand positioned vertically, but as your artist, maybe it's a rapper or something, lifts up a mic horizontally, that RF now is traveling through space on the opposite plane of what the receiver antenna is looking for. You get a dropout that looks like this, and this is why we need receiver diversity. There are many different types of diversity. The two basic ones are there are two receivers in a box. They're complete different receivers with complete different audio outputs, and then there's a switch looking at the RF level, and whichever receiver has the best RF, the audio switch sends that to the XLR output. And the other technique that we see a lot now is where you blend the two. I think Shure uses that, Electrosonics uses that. Pete,
James?
anybody else? Yeah, go ahead.
Yeah, David Michael Miller asks if he has his antennas set up for a one wavelength spacing, does the same 90-degree setup any significant improvement to diversity reception? In other words, putting one antenna 90 degrees out of the other antenna.
Absolutely. Anytime you have all systems just about, except small ENG type camera devices, and even some of those, pretty much all professional audio products now utilize diversity. And so anytime you have diversity, you absolutely want to take advantage of polarization. So what does that mean? That means that if you're using mic stands and they have boom poles, then set them up in sort of a V-like pattern. And yes, keep them about a wavelength apart for a lot of reasons, but also maybe they'll now be diagonal and facing opposite directions. In other words, the two antennas, if you put them together, would be perpendicular to each other, and now you're covering the greatest amount of polarization possibilities with that setup. Great question. Okay, let's talk about just antennas real quickly. These are all available pretty regularly through most manufacturers. Again, that center one is a dipole from Electrosonics. Pretty slick because it's got frequencies written on it, and you could just loosen up some set screws, set the center frequency of your system, and now you have a almost perfectly tuned dipole. Dipole antennas have a pattern like that one in the middle. It's called a donut reception pattern, and essentially what that means is that an antenna is practically aligned above it and below it, but perpendicular to it, it has the greatest gain, and that's simply because from that angle you have the greatest amount of surface area that the RF signal could see. The next set of antennas are pretty much what I utilize exclusively. I almost never use a whip antenna unless it's to do a radio sweep in an omni pattern. Almost never use whips. And as soon as you remove the whip, I'm going to say this now because we don't cover it later. As soon as you take a whip antenna off of the back of your receiver, there's only one place that should go, and that is back in the box or in the rack drawer. You cannot take a whip antenna and put it at the end of a 50-foot cable because that whip is only half of the antenna. You need two whips to create a dipole, which is now a self-contained remote antenna. The top unit there to the right you're looking at, log periodic dipole array. All that is an array of dipoles of different sizes, but they are self-contained. So that antenna will give you about 6 dB of gain. It's fairly directional. The antennas below that are multi-polarized antennas, and that's pretty much what I use exclusively. And the reason for that is if you look at that, any paddle, which by the way, that top log periodic dipole paddle, that is just simply what is etched on the PC board of your paddle. So if you're using a shark fin, whether it's from Shure or Electrosonics or PWS or Sennheiser or Audio-Technica or you name it, you look at it closely, you'll see etchings on the side of the antenna, and that's just simply exactly what you're looking at on this log periodic paddle, which is an old one made by a company called Vega before they were done on PC boards. Well, this is a great antenna, but it is kind of like an old grandfather clock that no one has wound in 100 years. You know, it's still right twice a day, right? If you want to get away from being right only twice out of your entire polarization possibility, you need to go to a multi-polarized antenna. Below that is a circularly polarized antenna. It's got Very similar gain and polar pattern to a typical paddle, except that it's taking advantage of multipolarization. That's either I'm looking at a Sennheiser or a PWS, I think, are the only two companies that manufacture that antenna. And I use those specifically on comms and in-ear monitors because it's got a wide pattern and a good amount of gain. And most of those devices are non-diversity. The bottom antenna is the helical. That's the granddaddy of them all. And that's the one I'll use on wireless microphones because you have two of those. They're very directional. They give you 12 dB of gain over a dipole, and they're multipolarized. So it's really the best antenna that you can use if you can get two of them, like in a diversity system. And Kelly mentioned earlier about the Secret Service wanting to know if our CP antenna was really a camera, and that's why. Look at that middle antenna on the right. You can see why the Secret Service might have thought it was a camera. And by the way, I was walking to a show in Las Vegas one time, and I was carrying that through the casino, walking past the card tables, and you bet I got some people's attention. So don't walk through a casino or anywhere else that people don't want to have on camera, because that looks way too much like a security camera. So now what you're looking at there is just simply another view. That one looks more specific. It'd be the Sennheiser. Well, it could be the PWS. I can't tell from this side. The one on the right, it's a Radioactive Designs CP antenna. It's got the same gain and polar characteristics, but it operates in VHF. We call it the to-go box because it looks like a to-go box, a radome assembly. On the inside of that, it's just a couple of cross-pole dipoles. It's also good for VHF, Electrosonics, IFB transmitters, and it's good for Shure wireless microphones. We use it for the Radioactive Designs belt pack receives.
James,
Yes,
in terms of wireless mics versus in-ear monitors, how would you pick what mic to use for each? What's the best antenna for in-ear monitors, for instance?
okay.
Javier Liberon wants to know that.
Yes, I use the circularly polarized antenna for in-ears, and that is because it has a wider polar pattern than a helical. And again, if you use the helical for in-ears, yeah, you're going to have a great signal as long as your artist is within the path of the footprint of that antenna. But the footprint of a helical antenna kind of looks like a big, huge pot leaf with about 9 leaves on it. It's got a big, huge center lobe, and then there's nothing, and then another side lobe and nothing, and then another side lobe and nothing. Whereas the CP antenna is much wider, and you never know where your artist is going to be running around a stage. So I use CPs. Incidentally, I put those CPs underneath the stage and get them as close to the artist as possible. And I put them on a drum kick mic stand, pointed up and out into the audience, so that if they run out into the audience, they get the gain out there too, and it just works fabulous.
Now, you didn't really touch on in circularly polarized whether they were left or right. John Williams wants to know, how does one need both? Can you mix and match? How do they interact?
That's a great question. Yes, absolutely. So all right or left, if we go back one graph there to where the helical antenna is, maybe it's, yeah, that one. So the bottom right and also the CP, you could tell all it is, you know, $25 in screen door parts and some copper ribbon, but it's tuned very accurately, and it's got to be wound very precisely, and that's why they're as pricey as they are. But that wind, and let me think, it's tough to tell from here, but that one looks to be left-handed.
Left.
So now what that simply means is that the antenna has a connection to the center pin of the BNC cable and needs to be wound, you know, in the clockwise outward. Now, here's where it's important to know when to use which polarization. First off, if you only have right hand or left hand antennas, you can't go wrong, right? You can't really mess it up. If you're using one antenna for in-ear transmits and 2 for mic receives, I would go with an opposite polarization for the in-ears. So in other words, 2 right-hand antennas for the mics and 1 for the ears, simply because you'll always be in a cross-pole situation and minimize your RF noise from the in-ear transmitter onto the wireless mic receives, right? And if you're using the system as a point-to-point system, in other words, let's say you have an in-ear, I think Shure you could put into a point-to-point mode where you use a PSM 1000 transmitter and a UHFR receiver, and you have to go in and change the tone code squelch to match the in-ear monitor. Well, you want to use two right-hand systems. Like you would think, wait a minute, James said left hand on an in-ear, right hand on a mic. That's if you're using them as two different systems. If you're using a transmitter as an in-ear monitor as a point-to-point system, then the receiver, wherever it is, you also need to use the right hand polarized. Whatever you're using on the transmit, you have to match it on the receive. And if you ever forget that, just get a nut on a bolt and put two bolts end to end and rotate the nut off one bolt and onto the other, okay? If it doesn't work, then one's left-handed and one's right-handed. If the bolt goes smoothly from one to the next, then you've done it right.
I have a question also. What's the minimum distance you can use a helical antenna in? I was asked to come into a TV studio in New Jersey that was having problems with their RF. They only worked in certain places on the stage. And I went in, the ceiling was about a 12-foot ceiling, and they had a piece of tape on the floor in an X. And they said, this is the only place our wireless mics work. I walk over there, I look up, right above my head is a helical antenna shooting straight down at me. And they said, every time we walk away from this, it doesn't work.
Okay, that's a pretty funny one. So yeah, I mean, a helical antenna is a spotlight for wireless audio. So if you had a spotlight and you shined it from directly on the ceiling straight down, it's only going to work directly below it. If it's a small studio, you'd want to put that helical as far away on a wall as possible. And if you really have to put it in a lighting grid or on the ceiling of the studio, then a helical is not the right tool. A helical is not the right tool for a large studio where you're limited in where you could point that antenna. You would want the most omnidirectional antenna possible. The next one to look at might be a CP, but if you're saying you're trying to cover a large studio, then I would probably just use a dipole in the center of that studio in the ceiling, because 50 milliwatts, you should be able to cover a very, very large area.
So typically you see pictures of you doing the Super Bowl, you're off on the sideline and you have a forest of helical antennas shooting out to the middle of the field. That's the proper use for that kind of antenna.
That's exactly correct. And correctly, it's an antenna farm, right?
Exactly. Okay, it's not a forest.
We get lost through the woods and the forest, but yeah, that's an antenna farm. And you can't tell from the pictures, but all of the in-ear and comm transmit antennas will be on one side of the little RF audio area, and all of the receivers are on the other side.
That's a good point. Spacing of the antennas when you're using it. Typically, how far will you space receiver antennas, let's say diversity receiver antennas on the same receiver, and how far should it be from in-ear monitor antennas?
Okay, again, everything with wireless is a trade-off, and so you have to figure out how much room do I have to deal with. On the Super Bowl, I had the RF area, the comm area, and the mixer area. Tom Peaser or Mike Parker or somebody be down on the field. So there was a big audio. As you know, Pete, because you hired me for my first one, we had a very large sideline. Well, that was large for us back then. But still, it was only about what, maybe 20 feet, and we had to put that antenna farm. Okay, take that into consideration. And now the last show I worked on with Professional Wireless was a Latin show up in Miami for Univision called Premio Lo Nuestro. And there we could take advantage of an entire set of balcony seats backstage that were not used. So whereas on the Super Bowl, I might have had, 8 antennas in a 20-foot area, on a TV show where you have room to spread antennas out, we had that same number of antennas spread out over maybe 150 feet. So again, you have to consider how much room you have. Just know this, whatever the amount of space you have is, you need to keep your base transmit antennas as far from your base receive antennas as possible. The other part of that question involved diversity spacing. Again, use as much space as you have. when I do corporate events or some large music events where you have hundreds of feet, I'll usually put one helical antenna upstage, pointed out onto the stage and into the audience, because we have Q&A mics, we have people wanting to walk from the stage out in the audience. And then I'll put the second diversity antenna on a mic stand right next to me, where I could spin it around like a periscope and follow around the action if I need to.
We got a question right after you talked about circular polarization from Lisa Fehrenberger. Doesn't understand why alternating polarization matters depending on the way the coil is wound.
Okay, because the way a directional antenna works, like look at that helical antenna, for example. Actually, go up one from here then. Let's start with that. Go up one graphic, and you'll see, look at, for example, the dipole. What happens when you send energy into a piece of metal is it radiates out, right? It just radiates out. Now, if you go to the next graphic, what happens with the RF on a helical antenna is it's shooting through that coil, right? The way the RF wave comes out of the antenna right there that you're looking at is it's a 3/4 wave. It looks like 3/4 a wave of what you can see. Now, it's not a 3/4 wave antenna, but I'm trying to enable you to visualize what's going on here. That center cylinder is the active element, like a whip antenna, and the outer, the screen door, the metal screen door part, that's the ground plane, okay? So all you have here is a ground plane. The difference is the RF is spinning around this antenna and shooting out like a tornado, okay? And so the RF is literally spinning through space several 100 million times per second. And so since it's spinning through space and it's spinning in, let's just say, a clockwise direction, the receiver antenna has to pick it up in that same direction. Whereas if you put an opposite polarized antenna out there, the signal will barely be seen because it's spinning in a way, picture it as one static wave that's spinning around in space. I really need to come up with a graphic for this because that's a great question. But just picture the RF as literally spinning off of that antenna millions of times per second, and you have to match up the receiver antenna to get 100% energy transfer. And if anyone wants to get a little deeper into that and email me, I will try my best to find a graphic, or maybe somebody has one and can send it in, because I need to be able to describe that better. That's a great question. You're muted, Pete. I don't hear you anyway.
Sorry about that. Muted my mic. Wrong audio operator on this console. We have a request from James to turn on your cameras because they want to see you talking. But
oh boy,
yeah, they don't want to look at all these antennas and stuff. They want to look at James and the antennas. So
right. Stick me in some small corner somewhere.
Oh, you're right off to the side in a little itsy bitsy tiny window, so it's not like we're taking over the whole screen.
Okay,
now,
I can't see it.
From one of the other world-class RF persons in this country, Jason Glass, wants to touch on, instead of separating your transmit and receives antennas far apart, is there any advantage to putting a transmit antenna in the null of the RX antenna, let's say behind your paddle for receive? Put your transmit shooting at the back of a receive antenna?
Yeah, that's a great question. So that's in fact what I do. And the reason for that is with a helical, at least, for example, well, every directional antenna has a characteristic front to back ratio. It's got forward gain. In the case of the helical, that's 12 dB over dipole. And it has a front to back ratio. And in the case of the helical, that's 30 dB, 30 dB. And what that means is that antenna is practically blind behind it, okay? So when I set up RF in-ears and microphones, if I have to absolutely put one in front of the other, I put the receiver antenna in front, and then I put the transmitter antenna as far behind it as I can get, because we're taking advantage of the front to back ratio of the receiver antenna. If you do it the other way around, then that 12 dB of forward gain that you're realizing off of that helical antenna on the receiver is going to amplify the RF from the in-ear monitor transmitter, right? So it's going to amplify that, create noise on top of the wideband splitter you're using, and potentially cause dropouts, minimize your range, affect your audio quality, create interference. So if I have to choose, and it's better if you don't have to make this choice, but if you do, I would put the receiver antenna in front, as long as you're using helical antennas or some directional antenna. If you're using omnis, then it really doesn't matter because they're just some distance from each other, right? So if you have to absolutely use an in-ear system and a mic system and put one in front of the other as opposed to side or with more separation, again, put the receiver antenna in front and the transmit behind.
I think at this point we have to forego looking at you because it's eating up too much bandwidth. We'd rather hear good audio from you. So I'll sit here and move my mouth and try to lip sync with what you're saying. We did have one other question, another about the pattern of the antennas, and one use that I use if I'm trying to find out where somebody's transmitting from. I have a rogue frequency and I want to find it. I use a paddle, which is almost no reception ability from the rear at all. And I aim the back of that paddle around the room until I see the signal go away totally from my receiver. And that way I know they're off in this direction. So I don't use the front of the paddle because that's a very wide reception, but the back of the paddle is really sharp.
Yeah, that's a great point, Pete. Matter of fact, it was one of the Super Bowls where the NFL actually came down to the field and asked my crew to help them find an interfering signal. And Vern Sullivan, who was really a great engineering technician at Professional Wireless Systems, designed a homemade, Vern-made spiral antenna. And using his spiral antenna, he was able to shoot the antenna up and find that the interference was the result of two IFB transmitters that were a little too close to each other, creating an intermod third. And this antenna was so accurate that from the field, he looked up at the banners and said, this is coming from that suite that's in above the T in Miller time. So go to where it says the T in Miller time. That's the suite where it's coming from. He and my dad were on the field. And that spiral antenna, in fact, uses a null to direction find, not a peak signal. And it does exactly as you said. Now, of course, it would have to be a very strong signal at that point to use the null. Generally, you can get in the ballpark by using a directional paddle. You'd also need some type of portable spectrum analyzer, and we're going to get into spectrum analyzers and stuff here. In fact, I may skip some of the stuff coming up to get to that because that's real practical. But anyway, yes, you would need some type of monitoring device, and it needs to be portable because you need to walk around. I remember it was one of the Super Bowls. I was getting stepped on. It was during a rehearsal. It was on the choreographer's mic, and it was coming out of a 500,000 watt sound system, RF dropouts. And so I had to run with a portable analyzer and a directional paddle. We located the guy in about a minute. He was walking onto the field with a transmitter in his pocket, and I told him, I said, you have a transmitter on 585 dot whatever, and he goes, no, I don't. It's off. And I used the paddle, and I said, well, it's in your left pocket. And that's when he started to sweat and realized he did come in with the transmitter on. But yeah, you'd need a paddle, you'd need some type of portable monitoring device, a scanner, a freak counter, or a spectrum analyzer, and we're going to go over a couple here in a bit.
Before we leave antennas, talk about the antennas from the Omni to the paddle to the dome to the helical antenna, and how wide a distance can you reliably use that in before your audience walks out of the pickup area? This is a question Jason Glass suggested.
Great. Hey, hi, Jason, by the way. Thanks for joining us. Always has great questions. So there are a couple of things to consider when you're using an antenna. The first thing is, excuse me, anytime you get range, I'm sorry, anytime you get gain out of an antenna, you lose polar pattern. Okay, as I said, everything to do with wireless audio is a trade-off. If you get if there's no gain, then you get omnidirectional reception. As soon as you begin to ask for a little bit of gain, in other words, forward gain, that means that you're going to establish a footprint of some kind, just like a microphone, just like a speaker, just like a spotlight. Not in general, all the time, every time, the more gain you get out of an antenna, the tighter the polar pattern. Now, if we look at the antennas that are on the screen here, the gain that you get from the paddle antenna, which again is the top one, and the middle one, the circularly polarized antenna, the gain is identical because the polar pattern, because the footprint is identical, okay? The gain of the helical on the bottom is 4 times better than those other 2 antennas, but the pattern is 4 times tighter. You see what I mean? So you cannot get gain without directionality. You cannot establish gain without building a tighter and tighter footprint from your antenna.
One last little thing from Jeremy Goldstein. He's talking about using a passive radiated helicals or CP to extend your coverage area. And we did this once at a Super Bowl outside the VOM going onto the field, and to the right was the production compound. And we took a Yagi, just like the top paddle up here, at the field of the edge of the field, shooting out into the field, and ran a 100-foot RG8 cable around the corner and put a Yagi outside of it, basically antenna to antenna. And at that time, we were using HME wireless bell packs. And that effectively allowed an easy path for the RF to get around the corner, worked fine. It's not a panacea, but in the right situation, it sometimes helps.
Yeah, that's really cool too. That's called a passive repeater. It won't work in free space. It's not going to extend your range in an open field or at a festival. But if the reason you're losing range is because there's some type of RF shadowing, in other words, you're inside of a stadium versus outside, or you're down in a manhole or going through a tunnel. Okay, you literally use a gain antenna to grab the RF while it has a good level. You shoot it down this RF coax cable and then drop it out of another gain antenna to cover the area that you'd like covered. And you literally are building a passive repeater. There's no electronic parts. You don't have to plug it into a wall. It's using the RF, the physics of RF and passive gain to grab an RF from one area and shoot it down a cable and distribute it to another area. Very cool. I use that not a lot, but there's certainly times for it. And it's obviously not very expensive because it's just a cable and 2 antennas. It just doesn't work in an open field, in an open area. You have to have some reason to grab RF from one area and shoot it somewhere else. Okay, free coordination. We can go kind of deep into this, but I believe we're going to try to organize a PWS possible RAD, Epperson, Care, Erskine presentation over the next week, and we'll get deep into probably IAS. But in general, there's a need to coordinate frequencies. As soon as the second wireless microphone was introduced on the planet, we needed to start coordinating, right? So if you go down one graph, we're gonna talk about free coordination here for a couple of minutes. I'll try to blow through it because I still have quite a bit of material. So go to the one right above that just for a sec. This is just 35 megahertz off of a spectrum analyzer. All it is a portion of the in-ear monitor and base station comm transmitter. The signal down to the left is a 6 meg DTV signal. This sweep was taken inside of an arena, and that's why the DTV is attenuated in comparison to those signals. But obviously, any big show now, that's what an RF spectrum analyzer is going to look like, because we have very little space to operate in anymore. And in addition to just straight coordination, if you go down one to the intermod graph, this explains what happens when you light off 2 wireless microphones in one area. This is from Joe Cialdelli at Sennheiser, and as a matter of fact, this is from the 80s. Joe presented this materially in a wireless mic manual he wrote back in the late 80s when I first met him. And as you see back then, everything was VHF. There was no UHF. So this is when VHF was the only system. There weren't any UHF systems, and before all of the frequencies moved up to UHF, and now VHF is clear again, like the bar that nobody goes to because it was always too crowded. So what happens when you light off 2 radio transmitters, they essentially transmit into each other. They transmit, and because they're made out of nonlinear electronic parts, you know, NP junctions, diodes, transistors, this type of thing, the frequencies mix. And when the frequencies mix, you come up with the sum, the difference in the 2 originals. They get amplified again in their final RF amplifier, which is generally a very wideband device. And so you get this Christmas tree effect where you'll see the 2 products and then all of the intermod products. And you can never stop intermods from happening. At best, you are able to coordinate for those and avoid them. There's no way to prevent the intermod, but you can certainly avoid those using calculation software.
Now, why is intermodulation less of an issue with digital transmitters?
Yeah, that's a great question, and there's a couple of answers. A couple of correct answers. The first one is that, in general, digital systems are newer and are utilizing newer, better-made components, including all of the, the DSPs, the final RF amps. They're just better quality and, by nature, a little more linear than the older equipment. The second thing is, if you look, again, if you want to go back to this, Pete, feel welcome, but you'll see that an FM or AM signal is a razor sharp carrier, whereas a digital signal is the same amount of energy but spread out over 220 kilohertz or so. So even though the signal looks as strong, the energy envelope is equivalent, but it's spread out over, again, over 200K as opposed to a razor sharp signal.
25.
And that's why intermod is worse in analog products. Yeah, there you go. So as you can see on the right there, that's more indicative of of what we see on our digital, like a Shure or a Sennheiser 6000 would be the screen on the right, and that's a digital carrier. And as you can see, the energy is spread out over 220K. Whereas if you go up one from there, Pete, you'll see that the FM signal is well, that looks spread out, but it's actually one single carrier that's moving really quickly. That's bad. We'll go down 2. The AM would be a better way to look at it. This is what you're looking at is not one. That's one static carrier. Okay, the FM you just looked at was one carrier, but moving, showing the occupied bandwidth. This is what an analog transmitter carrier looks like on an analyzer, unlike what's spread out on the digital signal. And if I confused anybody by putting up the FM carrier again, what you're seeing there is the full deviation swing of one single frequency, and that's why it looks like it's spread out. That spread happens over the course of time in relation to the frequency of the audio input at the microphone. Okay, so
one other question. A couple of questions regarding a Wizicom. What are they doing to minimize their intermod products? I know that on their transmitters, they do a terrific demo at NAB where they take 2 transmitters and hold them right next to each other, and there is no intermod visible on the spectrum analyzer. How do they do that?
Right. So Massimo, the owner of Wizicom, is first off just a brilliant engineer. Really fun guy. If you get him away from work, he's really becomes a lot more fun even. But he's a brilliant design engineer. He makes a very well-built product. And if anyone could correct me if I'm wrong here, but I believe part of the whole sales pitch and demo is that he uses a component called an isolator right at the antenna. And what an isolator is it's a one-way street sign for RF. In other words, the RF could leave the transmitter, but no RF could get back in. And if anyone is listening and knows that to be either true or false, because I can't remember exactly which company does that demo and says that it's because of the use of an isolator, and I also haven't seen a schematic of the transmitter, but one of them, and I think it's Massimo at Wizzycom, says that he puts mini isolators, little mini check valves, one-way streets for RF right at the antenna.
So basically, where you talked about the RF going back into the other transmitter and mixing with the electronics, he blocks that at the antenna.
That's exactly
so that,
correct.
So that it never gets into the electronics.
Yes. And if somebody knows if somebody could verify that, please do. I don't want to misspeak, but I'm pretty sure it is Wizzycom that makes that kind of, verifiably so, part of a good sales pitch, because it is a great component. Now, not every manufacturer says they need it, but on the other hand, not every manufacturer is transmitting a quarter watt. You start transmitting a quarter watt without the proper, proper design in place, and you could create intermods where you wouldn't normally have not had any. And so since Massimo and Wizzycom's transmitters put out so much power, I believe that's the company that did require this component, the isolator.
The Axion Digital and ULXD have a mode called ultra low power high density mode, where you don't have to do a frequency coordination. You just stack the frequencies one right after the other, fill the entire place up. How can they do that in low power mode? And when they do high power mode, you have to coordinate it.
Okay, that's a great question. First off, if you're using an Axion Digital and you have so many systems that you have to use that low power mode, the high density mode, then more than likely you're only using Axion Digitals. And so my point is that you're not combining all of these transmitters in another system's receiver, in other words, a wideband antenna splitter or an intercom receiver or something else, to have to worry about intermods. That's a little teeny piece of it. The bigger part of this is that it's a digital transmitter and thereby is less prone to intermod. And the second thing is because you're transmitting lower power, there's less of a chance for intermod. As you turn your power down, you decrease the chance for these intermod products. And so if you're transmitting, 40 signals at 250 milliwatts, it's going to be a mess. It's going to be a nightmare. You're creating a mess. There's no need to use a quarter watt. If you're able to get away with transmitting at 20 milliwatts, then you will greatly decrease your RF noise floor. You'll greatly decrease your intermod distortion products. And in fact, when I do a show, I keep all of my transmitters at 50 milliwatts. It doesn't matter how much range I need because I can make up for that range using a helical antenna on the receive side.
I recently coordinated a church in Chicago that had well over 200 wireless mics, but a lot of them were in meeting rooms. They would have like 4 to 6 mics in meeting rooms spread throughout the entire facility. And they were all ULXD. We elected to do every meeting room in high density mode, low power, and actually put them on channels that had weak DTV stations and left the totally clear channels for their Axion Digital in their main theater. And we were able to fit 200 in a very crowded spectrum, which is Chicago, without any real problem with that method.
Yeah, that's great. That's a great way to do that. And in fact, you're right. If you didn't do that, you probably would not have been able to get 200 frequencies in one space. I play that trick when I work as just a coordinator and not have to actually carry any cable, or like for the Rose Bowl, I'm just a coordinator. I don't operate wireless mics. But in IAS, which is a professional wireless coordination tool, which hopefully we'll get to talk about over the next week in a different webinar, there you can create different zones. So for example, I'll have the production, 40 or 50 RFs as one zone, and then I'll put one of the coach teams in one zone, the other coach team in another zone, ESPN college game day set in a different zone, and the ref mic in a different zone, because essentially they're all separated by 50 yards or so, right? So if everything's not right on top of each other, there's no, first off, it'd be almost impossible to get a clean coordination anyway. Secondly, you probably won't realize any intermod products from two units that are 50 yards apart. In fact, you won't, that's a fact. I'm not saying probably, it is a fact. So anyway, the trick that you played and the trick that you can use tools like, I don't know if Wireless Workbench has such a feature. Someone could certainly let us know with the question send in if they are aware. But I use the PWS software because I helped write it. But anyway, and it's a good tool, and that's the function that I'll use is the multi-zone function. Okay, and again, this all brings home the point that we have to start playing every trick in the book to be successful at wireless. We have to do all we can to maximize our chances for success. And so the big part of that, as I said at the head of this, was keep your RF noise floor low. And the way you keep your RF noise floor low is spreading out devices as far in frequency as you possibly can to minimize the RF noise floor to increase your own range and your own audio quality. Now, this is an RF spectrum band plan that I send to anyone who's operating on a show or an event where I'm the coordinator. And if you come in and try to light off, an IFB system up in the wireless mic band, no is a complete sentence for me. No. You have plenty of places to put IFBs now outside of the wireless mic spectrum. We have to protect the wireless mics because that's the on-air part and it's the most critical. This RF spectrum band plan is based on equipment that's available right now on the market. For example, 72 to 88 meg, or if you want to be technical, 76 to 88 meg. You could put Comtech IFB transmitters, that's TV5 and 6. 7 through 13, which is clear in almost every city. I mean, T-Mobile has energized through most counties. As Henry Cohn reminded me this morning, we're in phase 9 of a 10-phase repack, and almost the entire United States has now repacked and the dirt is almost settled, which, by the way, I haven't mentioned it yet. The TV repack must be completed by July 2020, July 13th. So by July, T-Mobile will be lit, and any of the other auction winners will be lit, and it will be illegal for us as in the audio community to operate in spectrum that is you don't see in front of you in these bands that I'm putting into this band plan. So 7 through 13 is 174 to 216. That's where the Radioactive Designs belt packs transmit, and also where the Electrosonics IFB and Shure wireless mics transmit. Now realize this: if you're using Electrosonics IFB, Shure ULXD, and RAD intercoms in the VHF band, you will require a further RF band plan for VHF. Maybe you could say I'll leave my Electrosonics in TV 7 and 8, 174 to roughly 190 or so, and then say 192 to 216 could be the microphones and the intercom belt packs. So you have to you may require further coordination if you have IFBs and RAD belt packs and Shure wireless in the VHF band. But this is the broad spectrum band plan that's based on equipment. 470 to 608, everybody makes mics there. Audio, I just did a show recently. I had the new Audio-Technica mic operates in there. I had Electrosonics in there. I had Sennheiser digital. I had Sennheiser analog, Shure ADs. I had ULXDs. I had Axions. Pretty much whatever I had the in-ear monitors. In-ear monitors, I further broke this band down, and I used the 470 to 530 meg spectrum for just in-ear monitors, because you're creating an envelope of noise when you light off 16 or 24 in-ear monitors, and you'll want to keep that separate from your wireless microphones, or you end up stepping on your own wireless receivers. So 470 to 530 were in-ears, and then 545 and up were all of my microphones. 614 to 616 will remain a legal spectrum for the foreseeable future. That's that search for extraterrestrial intelligence guard band above 614. And we put our RAD PL transmitters there. You could also use that band for microphones and IFBs or in-ears. Go ahead, Pete.
Why is that channel 37 always so verboten to use for transmission? It's always grayed out in all your coordination stuff. And
Yes.
are we sure that aliens are going to really transmit on that band when they talk to us?
Well, I've been listening. I haven't heard any, but there's also medical telemetry. If an event has a police, fire, and rescue unit, they may have equipment in that spectrum, for example. And also, it is a reserved band. I mean, it's always a clean band. Back in the old days, and now I've had my 7 years that I can talk about this type of thing. I mean, we used to use that band regularly when we were indoors. You also were able to apply for a special temporary authority from the FCC to use 608 to 614 for an event for a week. That has now become illegal as of the last FCC regulations that apply to the 600 meg auction. But we used to use 608 to 614 regularly. In fact, I think I used it when I worked for you, Pete, on Super Bowl. Of course, again, now that's illegal, and we can't make use of that band. My guess is that eventually larger tech giants will get to take advantage of that band for white space devices, but you'd want to dig in a little deeper. I could certainly email Mark Bruner or Joe Chowdelli, who are more Spectrum Affairs related than I am.
Andrew McKenna had noted when we were talking about IMD products, it's just basically a function of physics, but the control of those products can be minimized the use of isolators and combiners, just the way Wizicom does in their units. So if you're designing your antenna, you can mitigate intermod issues with the careful design of your antenna system and using isolators and filters. Just recently, actually the last show I worked on this year before the whole world got shut down was Dell and Henry Cohen coordinated over 500 frequencies for this show in one convention center. And every day he would walk into a new theater and they said, oh, by the way, we have 40 more mics here. Oh, by the way, and he just kept adding, it just went like through the roof. And ultimately, he was able to make it all work. And it's just a matter of playing all the tricks that you know to fit things in.
Right. Yep, absolutely. And those days may be sort of coming to an end here a bit, unless we move to a completely different spectrum. And by the way, hello, Andrew. Nice to see you out there, or hear you out there, or know you're out there. It sounds like this webinar is old home week here. I'd like to just touch briefly, and again, this is just a precursor to a potential rad webinar this week, getting into audio matrixing and scene changes and the program and that type of thing. If we move to the next graph, and by the way, this I'm keeping as basic and generic as possible. Anybody who is interested in having an interactive webinar through Kelly and Pete and Mac specific to Radioactive Designs products, please email Kelly or one of the guys and let them know so that we can gauge how critical it is. We'll probably do a combination professional wireless and Radioactive Designs webinar, because both sort of go hand in hand from an accessory standpoint. And so just please email Pete or Mac or Kelly and let them know so we can get a read on if we're going to do that or not.
We got two notes, one from Andrew McKenna about coordination that is not only using IAS or wireless workbench to do your frequency. However, you can divide it up into time, like you have mic stuff used in the morning, works, and then in the afternoon, and you might have a venue that has ballroom F can use frequencies that are used in ballroom A, probably without a big deal, because wireless mics are not going so far. In-ear monitors might go further. Jason Glass also mentioned that T-Mobile was just granted an STA that lets them activate every unused band 71 in their system for the next 3 months, part of this whole shelter in place thing, I think, to make their their phones work better. So this basically makes the transition complete as of last week because of COVID-19.
That's exactly correct. In fact, Radioactive Design sent out a tech bulletin to that effect, and we did communicate with T-Mobile this morning. Henry Cohen, well, Mark from T-Mobile sent a few of us a communication, and Henry followed up, and basically, without getting into great detail or breaking any NDAs, I could just say that yes, T-Mobile has access to whatever they need up there. Specifically, I think they're using blocks A, which I believe was Dish. I could be wrong on that, but yeah, let's just look at the world as RF audio people at this point and say, yeah, the days of using above 608, other than the specified guard bands, are over, starting right now.
The NFL for years has had a terrific coordination program for the football games. And it actually started years and years ago when they had an intercom system that used like 32 or 64 frequencies per team, and they were all in the UHF band. And they obviously had to take a proactive effort to protect their own use of those frequencies. So they started a program for 2 or 3 years in the beginning. It was all volunteer coordinators, and we would go in and connect with every single press person everywhere. And it took a while, but by the 3rd or 4th or 5th season, we actually had the NFL security give us authorization to assist in kicking out press that were using frequencies that they had not coordinated. Ralph Beaver notes that they coordinate every band everywhere, but their coordination is a little different. They don't do intermod for everybody. They're doing this spacing, make sure everybody is spaced, everybody has their own frequency, everybody at the time of day and location is coordinated. It gets much more complicated for their Super Bowl coordination than a regular game, but typically people will have to coordinate in advance of getting to the site, and if they don't, they might as well leave their wireless transmitters in the truck. It's been a terrific program, and love being a part of it now.
Yeah, that's great. And hey, Ralph, nice to hear that you're on here too. That's great. I worked with Ralph for many years. First met when I was the free coordinator for the Society of Broadcast Engineers in Orlando. And Ralph was in charge of Tampa area, and we sort of met in the middle, halfway between Orlando and Tampa. And of course, I worked with Ralph over many Super Bowls. The first time that started was back, the coordination group started back at Super Bowl in 1996 when Carl Voss was in Phoenix, and the NFL, Jay Gerber approached Carl and asked if he would sort of solidify that program, and it immediately just grew from there. I mean, back then it was tough to get the word out. Believe it or not, we weren't all online at that point in time. And so there was a lot of phone calls. We would get to the field and have some practice war games between the NFL films people and the coaches. And I was doing, as you know, Pete, just the entertainment, the national anthem and the halftime show. And there would be times where literally, because as you pointed out, the coach comms were all called the Lombardi system between 470 and probably 806 meg back then.
Ralph did correct me that channel 37 is not for aliens. It's for communicating to and from certain satellites. But who knows? Maybe the aliens are in the satellites. I'm not entirely sure.
That's great. No, it's a great program. But I do remember in the early days where we would literally have to timeshare frequencies. In other words, the coach comm belt pack during halftime, they were changing batteries anyway. And so that's when we would use the halftime show RF, and then we would kill our in-ears and mics and maybe some of the comms right at the end of halftime when the coach's belt packs got batteried up and handed back out for the second half. And that's the time sharing that Andrew was talking about.
The wireless workbench and IAS both have a function called zones, which you can put frequencies in a different zone. And when you put a bunch of frequencies in one zone, it does the calculations for intermod and picks the correct frequencies there. But you may have another stage 100 feet away that is also using frequencies, but that's far enough away so your intermod on this stage is not really going to affect it. Or it might be a different time of the day. So you can create another zone, which then only calculates your intermod within those frequencies. Because intermod, if you have a lot of frequencies, at a certain point, your program will start saying, can't find any, no more room, can't do it. So the only way to do that is to separate them out. And one of the things I did in the olden days with BTRs, which we hardly use anymore now, I would put all of the receive frequencies for the belt packs in their own zone, which normally they're pushed to transmit anyway, so they're not going to really be on all the time. And it allowed me to get much more frequencies in my transmit and my other zones without having to worry about that.
I should point out also that when you do that zoning, you do the intermod for one zone. It does not intermod. It doesn't do the calculation for the other zones, but it does take the frequencies into consideration and avoids those frequencies by your specified number, 200 kilohertz, 300 kilohertz. So it is looking at the other stages. It's just not doing any math. Now, I'm gonna pick up the pace of this a bit because I have a lot of material and I want to leave time for questions. And this is just a teaser for the Radioactive Designs potential webinar. If we do one, again, email Kelly or Pete. So this is sort of why we came up with Radioactive Designs. When we did, first off, there weren't the type of digital systems that were on the market as they are now. So we were sort of looking to be more spectrally efficient and remain analog. But the question does come up a lot, what's the difference and what are the pros and cons? And everybody, they do have pros and cons. The main thing as an RF coordinator, you can coordinate any analog system that could be tuned could be coordinated, whereas digital systems are based on either Wi-Fi or DECT or some other ISM band that is more or less frequency hopping. And if you get interference, there's no way to retune that system. There's nowhere to really go, per se. Analog also is more like an FM or an AM broadcast transmitter that there's a million people driving around in cars. You could tune radios and they're all listening to one antenna. Same thing with the analog, with the Radioactive Designs or any analog compact. There's one transmit antenna and there's an unlimited number of belt packs that could operate off that antenna, as opposed to digital RF nodes where they get loaded down by some number of packs and you have to add antennas if you want to use more packs. You also could set priorities with analog. If, for example, let's say Ralph is doing a football game and a Part 74 licensee comes in and says, I want to use my RAD system and here's my Part 74 license. And then another person comes in and says, you know, I'm with the halftime show band and I want to use a RAD, but they don't have a license. Well, the person with the license gets priority and you can license. This is a licensable, analog is licensable and has priority.
Now, I have a note here from Henry Cohen that the National Science Foundation has said no way to Part 74. So I think they've disallowed Part 74 licensees for using that wireless mics.
Disallowed use for Part 74 for what? A specific spectrum or a specific type of user?
That's all that Henry said. Why don't you describe what Part 74 is? Describe what Part 74 is for the listeners.
Well, Part 74 is a license that pretty much anyone can get. It was originally intended really just for broadcasters, but because of all the auctions and selling off of spectrum, it was, I think the FCC realized that there were more people out there using wireless microphones than broadcasters. And so what they said was, if you operate more than 50 wireless systems, it could be a combination of microphones, in-ears, IFBs, and comms, then you're considered a professional user and now have access to obtaining a Part 74 license. What the Part 74 license does is, in a coordinator's eyes and in the FCC's eyes, it establishes you as a user that should be
James, I think we lost you. Are you back there?
And this is the thrill of live webcasting, right? James is broadcasting from an undisclosed location in beautiful, sunny somewhere. James will have you just log in. I see he just went offline. He'll come back and join us. I'm confident the phone is going.
I want to talk about a couple of
Yeah,
questions while he's coming on there.
please do.
Richard Stockton pointed out that he says to all RF technicians need to push this. There's a lot of sports other than NFL that don't have dedicated RF coordinators on the event, and it's hard for the RF usage there to be used. Now, typically, a press person, if they have good RF practices, will turn their receiver on first at whatever frequency it happens to be on and see if anybody's using it. And only then will they turn their transmitter on. A lot of people don't do that, so it's a problem. If you don't have a coordinator, you don't know where you can go. And the frequency coordinator on a show is there to protect the user. So if you want to use wireless mic there, seek out and find or ask in advance who's the frequency coordinator and contact them. That's to protect you, so you can get a frequency, sign up, put your name on it, and protect your event. In terms of doing a show with a lot of different frequencies, like the NFL does, you want to just establish a spacing where you can put it in. Let's say you will allow any frequency to be 400 kilohertz away from any other frequency. Now, obviously, some frequencies can be closer, some can be farther apart, but as a coordinator, you probably just pick a number and fill in the slots in your list. We are going to do a radioactive design and professional wireless webinar. The professional wireless webinar probably will be a combo WWB and IAS, which a lot of us use, but we will also have Shure come on and do their WWB specific webinar. What's
Hello?
the date for that, Henry?
Hey, we got James coming back on. We got you on voice here, James. We were just talking about some best practices, and I think we've got you. And you want to pick up here where we were at on the analog versus digital?
Okay, I can't see you, but I'll open my PowerPoint and talk along. Yeah, I don't know how long I was talking. I'm probably ranting on for 5 minutes. But
It was
anyway,
all great, I'm sure.
yeah,
But yeah,
yeah.
we were at the the pros and cons of analog versus digital, and I think we were in that operating range and the licensing. We are kind of wrapping the licensing and moving into what are some of the other differentiators that we should be mindful of as users.
So James, currently I'm on slide 27. Now I've gone on to designing an operational system.
There's a distinct possibility, Pete, that the aliens have intercepted this and all that good stuff. So as we're waiting for James to come back on, I'll maybe why don't you kind of talk about where we're at right now, Pete, in this slide.
Well, I want to go back to one question that Lauren
Yeah,
Sherman
right
brought
ahead.
up. The actual show of the Super Bowl did intermod all their frequencies, but the NFL, when they coordinate the game, does not do intermod. Like, they don't do intermod with every single press person. But the actual show, particularly if the important place to do intermod, the most important place is when you're using combiners to combine your transmitters, particularly on in-ear monitors. That's where your combiners, like your Shure combiners or whatever, are nonlinear electronics, and they're going to cause intermod. So you want to make sure you have those coordinated. So, but we did generally coordinate all the mics and ears. Do we have a date assigned for the Shure PWS webinar already?
Well, we have a Shure WWB. The wireless workbench will be next Friday, the 3rd.
Okay. Okay.
Will be where we dig into wireless workbench and
Right.
talk about this. So be tuning in for that. That'll be with Corey Peoples from Shure, and I'm sure he'll have some other guests.
Right. Right. Now, one of the things that you have to think about when you're on a site is what the other departments are doing there. Typically, other departments like video and lighting will have equipment that does cause interference. When video screens first appeared, they were notoriously bad. Years and years ago, I did a touring concert with Tim McGraw and Faith Hill, where the entire stage was a floor of video screens. And the floor radiated from 400 meg to 700 meg, 10 dB of extra noise standing above the floor. So it was really hard to make ears work. And I basically had to pick frequencies, walk the stage, pick frequencies, walk the stage, until I found a frequency that happened to be able to be walkable without dropping out. It was really hard. Took me from 8 a.m. until showtime, which is 6, 7 p.m. To get them all working. It was a terrible problem. And then the next year, when they did the tour, the floor manufacturer had figured out that BNCs were the wrong connector to use for all their video because they're very leaky, and they charged to TNCs, which is like a BNC, only it screws on and is much less RF radiation. So all of a sudden, the radiation from this floor, same manufacturer, went down to nothing, and it was great. And then years later, I was asked by a touring company to evaluate before they gave the contract to the video screen, and I thought this was very forward-looking of them, evaluate the RF of the screens they were thinking of using. And I went out and I measured the screens, one at PRG and one at Tate for the floor, and they were wonderful. They were really terrific. They had no RF to speak of except maybe out of the back of the screen a little bit. So I didn't have to worry about that. However, I will note that all screens are basically a wall against RF. So if I'm doing a show, particularly with intercom, I need to have intercom receiver antennas behind the screen, even if they're free speak or Bolero, and I need to have antennas in front of the screen, because put them on one side of the screen and it just blocks it all out. So that's one consideration. Lighting generates strong interference, and a video wall, this is a good example of when the video wall was really bad. Noise all over the place, and in the middle there, you see there's a couple of TV stations.
Right, and Pete, it's I think we got James back here. While we're at that LED wall, James, you mind weighing in on just where are we at dealing with all these sources of noise? And Pete brought up a really good point where we have the opportunity to interact with production differently than we probably have in the years past, right?
Yep, absolutely. So all this RF generates very low. Oh boy, I am back. Look at that. If we go back to the prior screen, that was taken off of a Shure spectrum monitor, and that's why there's that gap up at the top. That's Shure's didn't tune up there when they did that. This is a large video wall. I think Tim Veer said it was from a Rolling Stones tour or something. But all of this RF noise from these devices, all these man-made devices, it's very low level. It's very near field RF. So the way you get around that is all you got to do is move your receiver microphone antennas away from that wall. If you move it 30 feet away, you'll reduce that noise to practically non-existent and still be able to pick up the RF from your transmitters. It's not going to get any easier. In fact, I think it was you, Kelly, when we were working with the Pope, his gooseneck microphone was getting interference from some lighting power supplies. And we ended up having to wrap some wires in tin foil and play whatever tricks we can to reduce the noise onto the wired microphone, not even wireless. So the other trick is get the antenna as close to the performing artist as possible. This is Super Bowl 2010. I think it was in Miami. That's Carrie Underwood. I'm with you guys, right? Yeah.
You bet you are.
Okay. So yeah, I don't know how long I was talking earlier. And what you see down there next to Carrie Underwood is this girl was 18 years old. That's my daughter Elise. And before I had her run out on the field with this helical antenna, I was trying to operate without having to get out on the field because they generally don't like people in their camera shots. And back behind where I was, way behind where Elise and the group of people and the Army and the refs were, Carrie's mic was gone completely, both channels gone. We were taking hits like crazy. And Tom Pisa, the monitor mixer, says, James, are we going to have our first failure of the national anthem at Super Bowl? And I'm like, no, Tom, we're not. So I grabbed helical and had Elise run out there. And I said, just go as far as you can until the cameraman tells you you're in his shot, stop, and then keep going another 30 feet till you run out of cable. And sure enough, the cameraman told her she was in the shot, and that's a live broadcast. But we were running off of one side of the diversity system of the wireless mic from Carrie, and it was pegged, and nothing on the other side. So a lot of people say, James, if you had a choice of taking one helical antenna on one side and nothing on the other side, would you take that over two whip antennas on both sides? Absolutely, any day of the week, I'll take one helical on one side rather than two less antennas and having both of them. Because in this case, we got through it just fine. There's no reason to hop to the bad side of a diversity channel anyway, unless the primary side goes bad. And in this case, thankfully, it did not, and it was pegged the whole time. And so Elise got a real nice present that night. That was 10 years ago. Human bodies absolutely do absorb RF. Here's a situation where we have the front of house is out in the middle of this crowd, far away from the stage. I'm sure it worked great during rehearsals. And then as soon as that audience loaded in, they blocked those meat sacks, absorbed all of the RF from the stage, and they got no RF performance. Just keep that in mind, that human bodies affect.
A Paul Simon concert in Central Park. No, it was in near the World Fair site. And I had my receive antennas on either side of the stage on stands, just shooting across the stage. And all of a sudden in rehearsal, they say, okay, we're going to be interviewing somebody out in front of the front of house position. And I even aiming the antennas out to the house, nothing. So I grabbed the rigger and said, here, take this antenna, climb up the back of the video screen, which covered the entire width of the stage and the entire height, and clamp it onto the top, shooting down into the audience. It took them about 5 minutes to do that. By the antenna got up to the top of the video screen, bang, really rock solid, because I was shooting down into the audience then, and it worked fine.
Great stuff. Yeah, height definitely equals range, right? Hey, I want to fly through some of this because I know people want to eat dinner here pretty soon. If you look at the next one here, just it speaks to the transmitter to transmitter intermod and how to reduce that. I use metal trays. You could use tin foil. You can go to catering and get tin foil. You can go to the lighting people and get some black wrap, but now you're going to owe them a favor, so I don't recommend that. We have, these are professional wireless systems, and some of the larger higher end companies now are shipping their own transmitter. This is what it looks like. When you take that transmitter and outside of the containers, they create that level of intermod noise that you see in the faded line. When you put them into the trays, that bold line is how clean that your system gets. Now, where the gray area is in between those transmitters, you might want to use a wireless comm there, or an in-ear, or another mic somewhere. And by not having those transmitters in the tray, you'll create such an abundance of noise floor that you limit the number of wireless you can use. So now we're going to go through and maximize our chances for success. And I call this the RF war game. This is the final check you do. I do it before a show. I do it throughout the show. And if I have 100 wireless microphones, this only takes about a minute to do this test. So if you have 12 mics or 24 mics, it shouldn't take you more than about 40 seconds to do this check. And if you're going to have an RF problem during your event, you'll find that unmask itself during this RF war game. First off, coordinate, program all your devices, including your comms, your mics, your ears, IFBs. Turn all of your transmitters on and put them out, spread them to some reasonable, you don't bunch them all up together on one stage because that's generally not the way things will operate, but this is reasonable. They're a few feet apart here. As you can see, I set the antennas away from each other. They're about 3 feet apart. Turn everything on. Go to RF number 1, turn it off, and you should see RF number 1 receiver completely clean and all of the rest of your RFs pegged. If you have something between clean when the transmitter's off and pegged when the transmitter's on, then you have work to do. And then if that's fine, you turn that transmitter on, you go to RF2, same thing. It should be dead quiet with everything else on. You're presenting that receiver with a worst case scenario of the world, right? And if it's going to get an intermod interference from your other transmitters, it will unmask itself and veil itself right then. So that's the RF war game in a nutshell. I'll get deeper into that if anybody wants, but again, I have too much material here to try to get through in 10 minutes. You need some eyes and ears. If there's no way that anyone could see or perceive RF without some electronic piece of equipment. There are certain insects could see electromagnetism, bees and so forth. Mosquitoes see infrared, but as human beings, we cannot perceive it. You need some type of device. There are programs out there. Shure has one, Sennheiser, RF Venue. Just about every manufacturer has a RF interface software program, which is limited to you carrying around your laptop with you. And then there's portable devices. That's my preference because I might not want to carry my computer all over the place. There are other devices that are simply radios that interface to a computer, like the Foxhound and others. There are radio scanners. That's about the most basic form. And you can't demodulate a digital Shure or Sennheiser signal, but you could certainly see the RF. The TTI is a pretty well-priced product, and I've had many of those over the years. It's very accurate, and for the price, it actually does a great job. You can use it to direction find interference and so forth. And then we get into some, the next, this graphic here you're looking at more or less represents the absolute most economically priced and one of the more expensive spectrum analyzers. The RF Explorer, there's some great programs out there that really turn that into a beast. I mean, it's pretty accurate, and it's also portable. So if you're looking for strong signal and have a paddle antenna, you can actually direction find that interference. And you could also use it to log your frequencies, as you could with the Shure Wireless Workbench and other software programs. And then the higher end spectrum analyzers, like that Rode and Schwartz spectrum analyzer, those would be used to generate a signal using an RF signal generator. And you could literally use that to shoot your RF cable and test the cable. A lot of people say, James, why would I need to spend $9,000? Why can't I just use an ohm meter? Well, an ohm meter will tell you that you have DC continuity, that you have no resistance. What the spectrum analyzer and an RF signal generator does is it sweeps the cable. And so if there's a kink in the cable that passes DC with an ohm meter, but might trap or block or null a specific radio frequency, then that's when you find that using the tracking generator. And by the way, if your cable does notch out a specific frequency because of it's kinked, believe me, that will be the frequency of your most important wireless microphone that you intend to use.
My personal preference is the TTI, the more recent version. This shows the old version, but the TTI, which is a couple of $1,000, because it does a terrific job of doing a scan of your spectrum. And despite the fact that the FCC does a terrific job in maintaining their website, which is linked through IAS to the website and through WWB, it isn't always right for every place you go. And A lot of times you'll go to a city and the databases will say that there are a certain number of stations, but there'll be an extra one in the list there that it's not in the list yet, or there'll be the opposite. Things will be gone. So I like to do a spectrum scan of every site I get to before I get to, or try to find a spectrum scan somebody else has done before I have to travel to the city to get at least a rough idea of how they do. And when we get to our show on IAS and spectrum scans, I'll show you my website, which has thousands and thousands of cities all the way around the world with spectrum scans. So you can check out, okay, what's it going to be in Warsaw? What's it going to be in Sydney? You can look at scans that have been done by other people. But I always have a more professional unit like the Roden Schwartz there, because it obviously is easier to use. It's got a keypad. I can punch in the frequency and bang, go to a frequency. Or the one I have, the Field Fox, not only does it give me a keypad that I can look at the frequency, but I can have presets to go to different place. And in the Field Fox, I can do a split screen of the loss of a cable and the frequency response of a cable just by plugging in one coax and have the antenna at the other end. So it checks out my cable before I've even gone there. Now, the RF Explorer is very inexpensive, but if you use the software on your computer with it, it gives you great results, more like professional results than the little display on the front, which is next to worthless. But if you plug it into your computer, it's terrific.
I agree with all of that, by the way. I think we're wrapping this up. I think I hear my stomach rumbling, calling me. But are there any more questions that we could address while we?
Well, there are a lot of questions we didn't actually deal with. Let me just scan through and see if there's something we can go on. Is there any cheaper alternative to testing your RF cables?
Well, actually, RF Explorer, I think it's maybe about a $350 piece, but they do make a unit that's got an RF signal generator. Now, would I use it to tune a filter as I would with the Roden Schwartz? Probably not.
Well,
but
it doesn't have a generator, so you can't do that.
There is a version of the RF Explorer that does have a generator. Yeah, it's about a $400 unit, and it looks just like the one that we had up, except it's got a signal generator.
Right. Now, what do you do to select your cable for an antenna? What's the best option to do for your cable?
My go-to is always RG8. You know, a low loss RG8. You can run it for 100 to 125 feet without the use of an RF amplifier, and you always want to minimize the use of any active RF device like an RF amplifier, because that just raises your overall noise floor and creates problems that wouldn't be there if you were to go passively. So I use RG8, 9913, or a flexible version of RG8.
What's the maximum length you would consider using?
Without an RF amp? Well, first off, if you use a helical antenna, you get 12 dB of passive gain.
Right.
So I've gone 150 feet using a helical antenna with no RF amp and been just fine.
Now, what if you, let's say, use the little inline Shure RF antenna or an antenna with an amplifier on it? At what point do you want to turn that amplifier antenna on, turn that little amplifier on?
Okay, first off, and a lot of manufacturers are not going to like what I'm about to say, but I am not a fan at all of a paddle antenna that's got a built-in RF amplifier for many reasons. First off is it's attached right to the antenna, so you can't insert a filter. Take Shure, for example. The circuitry in the RF amplifier that's attached to that active antenna the same amplifier is sold in a box, in a separate accessory box. But in that case, you can buy or build, or whatever your way to get a filter is, and you can insert that filter between the antenna and the first active device, which is the RF amp. So I'm all in favor of using an RF amp when it is filtered. If you're going to buy an amplifier that goes from DC to daylight, then you're going to amplify the RF noise floor from the video wall. You're going to amplify the walkie-talkies that are keying up 5 feet away. You know, so I'm always one to use a filtered system, and a filter always goes between the antenna and the first active device. Same thing if you filter the output of a in-ear monitor transmit combiner. You can combine these transmitters and they'll create spurs, spurious emissions, but you can put a filter between that active device and the antenna, the transmit antenna. Yes, those spurs will be there, but they'll disappear inside of the filter and you'll get a much cleaner signal. So I'm all in favor. Yeah.
The newer Shure antenna that has a little switch with +6, 12, -6. I found if I use it in an area with high RF, like on 34th Street, where the Empire State Building is right there looking at me, even before I start using it, it says overload.
Yes.
Right. So I don't like to use any antenna that's amplified, and I do like when I get over 150 feet of antenna cable, then I will take the little Shure inline antenna and put it at the receiver. So the antenna cable is doing all this loss before it gets to the transmitter amplifier, and then amplifying right before the receiver.
So I do something really similar. I will run my antenna with a filter, and then maybe 25 or 50 feet of cable to lower the signal, and then put the amplifier, and then the longer part of the run would be at the output of the RF amp. But it's the concept is, if you put the amplifier right at the antenna, you will generally create noise, and that's why I'm not an advocate of paddles with built-in antennas. Built-in amplifiers.
If you're doing in-ear monitors and it's not covering the stage, would you ever put an amplifier in line with that in-ear monitor transmitter?
No, because an RF amp is designed for receiver only. Those amplifiers are meant for microvolts of energy.
No, I'm not talking about those. I mean, let's say a little microcircuits 1-watt amplifier that might stick on the output of your transmitter to try to get your in-ear monitor to cover the whole football field.
Yes, I've done precisely that many, many times, to the legal limit of the law, which is 250 milliwatts for a UHF in-ear monitor.
Right. But
I'm not talking about any other systems like that.
You will have a better chance making your coverage work if you pick a really quiet, low noise part of your spectrum to put your in-ear monitor in. It's if you're trying to fight that noise spectrum, it's not going to go very far.
Exactly, and that ties into my first opening comment, which is the lower your noise floor, the better your signal to noise ratio, the cleaner your audio, the better quality, and the greater range you get.
Right.
Yeah, mini circuits makes a nice, easy, off-the-shelf. I think it's ZHL-2 BNC is the model, if I remember correctly. Right. And you can buy 4 of those and combine them, and even with that 6 dB of loss, you still get your legal, 200 milliwatts or so. So yeah, if you need an amp, use it. But I've found before I increase my power, I look for a cleaner system, and that's why I do the RF war game, because the RF war game is going to make you look at your analyzer.
Oh, you'll definitely see if it's clear, right?
Yes.
Right. Way back in the beginning of the show, Thomas Halpin asks, do wireless mics have a specific polarization?
Well, that depends on the transmitter design. Sennheiser 5000s use a dipole. UHFRs have a little mini spiral antenna that's actually patented by Shure. One of the RF engineers at Shure designed it. I'm not sure if it was Dr. Mark Kenkel or one of those guys, but if you open it up, it's a miniature little helical. So the type of antenna used on a transmitter is specific to the manufacturer and their design.
John Stefanik asks, he has his little studio is about 50 by 50, 20-foot ceilings. What kind of antenna should he use in that studio?
Okay, if it's 50 by 50, I would probably just throw a ground plane antenna, hang it from the ceiling or if that's not convenient, then he can put a paddle on the side of the room where that's closest to the wireless microphone receivers. And that a 50-foot room, that'll cover the entire room. If it needs to be portable, he could throw the antenna on a couple of mic stands. I would not use an RF amplifier.
And one thing we didn't talk about is antenna systems. And Rafi Levin asked, is it better to hook up the antennas direct to one unit and then loop through to the next one? Well, antennas don't have a loop through.
Well, the ones
You gotta
that
use a
do,
combiner or a splitter along the way.
certain, Sennheiser and Shure do have a loop out on their receivers. They did
No, I'm talking about on the antennas. He was
Well,
saying loop through the antenna to the next one.
I believe what the intent was to go into one receiver and loop out into the next one. It's called daisy chaining, and I don't recommend it. I do not recommend it because in order to make up for the 3 dB loss on the loop out, there's an RF amplifier, which adds a little bit of noise, which I've done it on if I had to connect one system to another. But you go much beyond 2 receivers looping through being daisy chained, that RF amplifier noise begins to add up, and by the bottom receiver, you're going to have so much noise that last receiver in the daisy chain will be dropping out and noising up while the top main unit is in perfect condition.
Now, if I put a helical antenna here with a 25-foot cable to my receiver, am I going to overload the input of that receiver? If my performer is 50, 60, 100 feet out?
No, because wireless mic receivers are really pretty incredible devices. They have an incredible amount of dynamic range. They can operate from a couple of microvolts to 1,000 microvolts, right? It's an incredible amount of dynamic range. And so you're not going to, in that situation, overload the front end of a receiver. In fact, if you only have 2 or 3 channels of microphones and you have a helical antenna, there's so much gain in the helical that you can use passive splitters which have no noise whatsoever to feed to those 4 receivers.
Now,
Hey, Pete,
do you see
I
any?
need to jump in here real quick, buddy.
Go ahead,
Sorry
Kelly.
to do this. Let's do one more question because I know James has got another commitment, and I want to honor our time frame here.
Oh, right.
Obviously, everybody loves this.
Quick answer. What's the mini circuit model number again for Chopper?
Hey, Chopper, it's Zebra Hotel Lima, ZHL-2-4, or you can just go to Mini Circuit's website. That's the one I've used for, I don't know, 20 years. They might have something newer. I'm sure they do. They make RF amps that'll take 13 dBm, which is about 20 milliwatts, and kick it up to 800 milliwatts. Of course, we're not legally allowed to go past 250, and you generally don't even require that much. But just go to Mini Circuit's website. If you have a question, shoot me an email. I will get back to you. And in fact, there's a real good chance I'll have little else to do over the next couple of weeks. So you'll probably get an answer sooner than usual from me on an email.
So I'm going to say there's a lot of cool other topics that we need to get into at some point. When we get to PWS or RAD, we're gonna probably talk about RF over fiber. We're gonna talk about combiners, distribution systems. I mean, my phone's like blowing up right now with everything, right? It's James Stoffo. It's hot. RF is always hot, no matter when it is in time of year. And thank you, James, for being a part of this. I want to remind everybody as we're getting ready to wrap up here, March 31, Lunch with Pete is all about RF coordination. All right. Pete, he loves his paperwork. We've got that this week, which is show prep, but next week will be all about that. That'll lead us into.
Next week, I'm going to go through the whole process of going on tour, using my TTA to scan the city, plugging my frequencies into IAS, looking at them on the Field Fox on the venue, plugging them into wireless workbench to control my entire system. The whole process.
And that's all before we have James again. So obviously, we know everybody loves this one. Next week is going to be a crazy week. I'm just telling you that right now. We've got wireless workbench at the end of the week. We've got field applications with Bill Salzer from East Shore Sound, Rito Clearcom cross-platform. It's super cool. We've got Unity coming up. let's see, I'm looking over here. I've got HelixNet on Thursday with LQ and Agent IC and Ron Rosenblum again. And we're even doing overnights next week with Asia and Middle East with all kinds of topics. So you know what? There's no sense in going back to work. We're just not going to go to bed, and we're going to just do as many things as we can do right now.
Hey,
Pete, you want to say something?
if you're hooked on these webinars, go to the 1 a.m. and the 2 a.m. shows too, which we're doing for Asia.
There you go.
They're going to be basically Shure centric. So
Those are ClearCom. Those are ClearCom topics.
isn't
Right.
Shure and ClearCom the same company? I don't know.
No, not this week.
No.
So anyhow, thanks again to everybody who joined us. James, thanks so much. I know you got a million things going on. You're working on the house. Thank you for joining us with this. Mac, any closing thoughts you'd like to share?
And nothing to offer except gratitude to James for really presenting a tremendous amount of information in 2 hours.
Yeah, man, thank you so much. Thank you, everybody that was listening. Keep an eye out for practicalshowtech.com. We keep everything updated. Yes, this will be available for viewing on demand probably by tomorrow. So if you missed some of it, if buffering, whatever, go back, see it every episode.
In a couple of weeks, we're going to do a show with James from 30 feet to maximum recreational depth, doing RF under the water. There we go.
Hey,
And there's the ultimate tease. Everybody have a great night. Thanks again for joining us. So long.
Bye-bye.
Bye-bye.